Right, so to be able to answer this question, you need to understand a bit about springs. Not too much, but here we can see someone jumping on the trampoline. So when they're in the air, the springs are stretched less. And when she lands on it, she stretches the springs more. So you can see that the elastic potential of each spring is 4.9 joules at position A when she's not stretching them. And it increases to 8.1 joules as the springs are stretched more as she's got a weight on the trampoline. Now the springs, all springs have something called a spring constant. And that spring constant basically tells you how hard it is to stretch a spring. Okay? That's what spring constant means, how hard it is to stretch a spring. Now, no matter what happens, no matter what changes, that spring constant is always going to remain the same. Okay? So what we need to do first of all is work out what that spring constant is, and then we can use that throughout the whole question. So K represents spring constant. Now you can see that the elastic potential energy of each spring is 4.9 joules. So the fact we're told the elastic potential energy means we're definitely going to be using an equation with elastic potential energy. So we've got to find that equation. So hopefully you can see it's not that one, but it is this one, and it's there. Elastic potential energy equals half the spring constant times by extension squared. So let's see FIFA it. Let's put our C FIFA down, like so. And then let's put down what we know. So we know we want to work out what the spring constant is, because that will be really useful in this calculation when we're talking about springs. We know the elastic potential energy, okay, and we know the trampoline is stretched. So the stretched means it gets extended. So that matches up to the E on here, the extension. Okay, so there's nothing to convert, so we'll leave that there, and we write that equation down. So elastic potential energy equals half of the spring constant times by extension squared. Now, it says when the child's at position A, each trampoline spring is stretched by 0.056 meters. So that's relevant to position A. The elastic potential of each spring is 4.9 joules, which is relevant to position A. So we know two things from position A. When the charge is at position B, the elastic potential energy of each spring increases to 8.1. So that is relevant to position B. So we know two things for position A, but we only know one thing for position B. So this is going to be relevant to position A because we know the two things for it. So what we're going to do is we're going to replace the letters with numbers. So for position A, because we're going to use this as position A because we know more things for position A than we do for B, we know the elastic potential energy is 4.9 joules, and we know that we don't know the half the spring constant, but we do know the extension squared. So the extension is 0.056. So 0.056, and then I'm going to square it. That gives us 3.136 times 10 to the minus 3. So 3.136 times 10 to the minus 3. Okay, you might as well keep it like that. Don't bother converting it to a number because you're just going to increase your chances of making a mistake. So what we need to do now is find the spring constant, because the spring constant then will help us with this bit. Okay, so what we do is we rearrange for the spring constant. So 4.9 equals half the spring constant times by the extension squared, which is 3.136 times 10 to the minus 3. We want to get half of the spring constant on its own. Okay, so we divide by 3.136 times 10 to the minus 3. What if we do to the right? We do to the left. So 3.136 times 10 to the minus 3. That cancels that. So what we end up with is 4.9 divided by 3.136 times 10 to the minus 3. Okay, and that will give us half the spring constant. So we will put that into a calculator. Remember, we're dividing, so we use the fraction button. So 4.9 divided by 3.136 times by 10 to the minus 3. And then check that's right. Looks right to me. And we have a look at our answers. 1562.5. Now remember, that gives us half the spring constant. So to get the full spring constant, that's only half our value. So we times it by 2 to give us our full spring constant. So we times by 2, that gives us 3125. That's a really nice number. That usually an indication we're along the right lines. So that equals K. So we know K is 3125. Okay? So now what we need to do is work it out for B, because calculate the extension of each spring when the child is at position B. Okay? So we're going to see phi for it again, but we're going to see phi for it for B. So C, F, I, F, A. Okay, now we don't need to convert anything, and we're just going to use the same equation again. So we're going to write E equals half the K, which is the spring constant, times by extension squared. Replace the letters with numbers. So we know at B it's 8.1 joules, okay, equals half of K. So we know 3125 is K because that's the spring constant we worked out here. So we divide it by 2 to get our half our spring constant. So that is 1562.5 times by extension squared. Remember, we don't know the extension, we only know the extension for A is after the extension for B. So all we need to do now is rearrange that for E. So 8.1 equals 1562.5 times by E squared. We want to get E squared on its own, so we divide by 1562.5 because we're times in by 1562.5, so we divide to undo that. Whatever we do to the left, we do to the right, or whatever we do to the right, so we do to the left. Okay, that cancels, that cancels. So what we end up with is 8.1 divided by 1562.5 gives us E squared. Okay, so let's do that quickly on our calculator using the fraction button. 8.1 divided by 1562.5 gives us 5.184 times by 10 to the minus 3. Now that's the extension squared, but what we want is just the extension, so we square root that. So we put our square root in. 5.184 times by 10 to the minus 3, that gives us 0.072, which is quite a nice number, which is an indication we are right. Hopefully that is clear. There it is on there, sorry. Thank you.